So it's good that we did the proof in one shot. That makes the logic flow better. Okay, so any questions? At least you know what we have done. That is more important. Okay, there are technical details, maybe one step you don't follow entirely, but at least the big picture. 6 commutation relations of angular momentum in general enforces some very interesting criteria on the eigenvalues of the length, particular form, and eigenvalue of the Z component, and possible number of it. Okay. You mean this integer? That is not a problem because J is that particular integer, you see? I just rewrite it as J. So you are asking, then the question becomes, what does J mean? And that has to do with the length of the angular momentum that we are concerning. Okay. Okay, so let me continue on just with a first remark. What we have done is the general statements. The most important thing is that only 2 possibilities, half integer for J or integers for J. We have seen examples of these 2 options. Electron spin half, that is this case. Orbital angular momentum, we have different possible S state, P state, and D states. They take on integer. Then you may wonder, why, when you solve the hydrogen atom problem, the theta phi problem, only integer orbital angular momentum quantum numbers are allowed. Only S, L equals 0, P, L equals 1, etc. If you remember what you did, you write that in the realization of a real space, theta phi. All right? And the L square and LZ operator can be written as some derivatives in theta and phi. For example, the LZ component is IH bar D d phi. Okay? And then you solve it as EIM phi. And you have this ML quantum number comes in. So far, so good. But then, in doing this particular orbital angular momentum within the central force problems, you are enforcing one additional physical requirement. You are enforcing that it should be single valued. Therefore, when you solve the EIML phi, the Z component of the angular momentum eigenstate, you say, start here phi, go through 2 pi, come back here, the wave function should be the same. And therefore, suddenly, you require the Z components to only take on an integer times H bar. Therefore, you are choosing a particular option. But there's no contradiction here because in this problem, there's an additional requirement. That is to say, from the options, you pick the one that your additional single value in real space requirement is satisfied. Okay, so nothing in contradiction. And you have seen the electron case that we discussed last time. So that is the J equals half, but it's so important that we will call it S instead. Another remark is that in higher level writing, a more abstract way of writing this result is the following. We will refer to the JZ eigenvalue simply as MJ, okay? And then the highest J will give us the J square eigenvalue. Thereby, we can abstract, in an abstract way, label this JMJ as the simultaneous eigenstate. This is our phi that has J square eigenvalue being J times J plus 1 H bar square. We prove it, it must take on this form, and JZ, when this second quantum number is MJ, it will give us MJ H bar. Hidden behind, given a J, MJ goes from plus J to minus J in step of 1. Thereby, the Z components start from JH bar to minus JH bar in step of H bar. That is what we prove, okay? So this box is what you usually see in more advanced formal quantum mechanics books. The last comment, and I will stop after this page playing with general. Why J isn't the sum of, oh, not yet. Here, a student asks, why isn't the sum of L plus spin angular momentum, what he's asking is the symbol, actually. Why J isn't the sum of L plus spin and quantum number, all right? And J should be orbital. Yes, that will come later, all right? But at this point, you must understand, we are simply using the symbol J for arbitrary angular momentum in quantum mechanics. Is that okay? Not yet. Starting this page, it will be, okay? But here, the context is different, okay? Now, this will be the last page of some formal thing that will lead you, at least point to you, where you can read a little bit more, okay? So, in this notation, JMJ, this abstract notation, we have shown if we operate J plus on it, it will increase the Z component. So it will bring us to JMJ plus 1, okay? H bar higher in the Z component, okay? So it is true, we have proven that this will take the eigenstate into a new eigenstate with quantum number MJ plus 1. So we can only work it out up to a proportional constant. You may wonder, what is it equal to something in front? Okay, what is the proportionality constant? Similarly, we know that J minus operate on this state will take the Z component minus 1 down. Okay, that is minus H bar down, okay? So we know that it is proportional. You may wonder, what is the constant in front? Okay, and that is the details about quantum mechanical angular momenta. We can work this thing out, okay? I lost a page number because I numbered the page after I write this page, okay? Sorry, I will fill it in, okay? But I copied the formula here. We have something like that, okay? And using that, actually we can work of this proportionality constants. Okay, for example, if you operate this, that is to say, you first increase mj by 1, then you will decrease mj by 1 again. Of course, after that, you will take it back to this state. But every time you do something, you have a proportionality constant in front. And in this case, you can use this operator relation to work out something rather scaring. You get this proportionality constant, okay? And using that, actually, you can work out what is the proportionality constant here and there, okay? But that is beyond the scope of our course. That will be quantum mechanics 2, okay? But at least I take you there and then let you go, okay? So if you want to work it out, I think you can work it out, okay? So that is the end of this proof. So let's go back to a more ordinary thing. What we did in the last section is to prepare us to look at other possible angular momentum. So obviously, some of you, at least I know one student know that, there is something called L plus S, total angular momentum, okay? But so far, if you follow quantum mechanics 1 up to here, you have seen things like orbital angular momentum in solving hydrogen atom, central forces problems. You have seen the spin of the electron, Stern-Gerlach experiment. So you have seen 2 angular momenta separately. And that motivated us to see whether we can add 2 angular momenta together to form a new angular momentum that we call total angular momentum. Okay, so here we will first discuss the rule to add them. We are not going to prove the rule because proving it is a much harder thing to do. That has to do with a chapter called addition of angular momentum in quantum mechanics. That is quite abstract and rather, well, it's not easy. I would not say it's difficult, but it's not easy, okay? But you will do that if you go to the next course in quantum mechanics. But the way to do it, I mean, what is the rule to add to is easy to execute. So here, I will list out the rule to add 2 angular momentum. Therefore, you can add 3, add 4, because you can do 1 add to 2, and then you have a total of 1 and 2, and then this add to the 3rd one, then you have another one, and then add to the 4th one, you have another one. Thereby, the crucial thing is to know how to add 2 angular momentum. And we have a concrete example in hand, right? So let me motivate the problem. Even hydrogen. In a hydrogen state, Schrödinger equation solutions will carry 3 quantum numbers because it's a 3D spatial problem, okay? You have a principal quantum number n, you have the LML. And this LML actually goes with the orbital angular momentum. That's fine. And Pauli said, there is a 4th quantum number that could be plus minus half. But last time, we explained that actually there is a 5th quantum number because what Pauli said has to do with electrons' spin. And spin formally is an angular momentum. So the formal word is spin angular momentum. And you have this Pauli matrices in the last course. And if you work out the commutation, they obey this 6 commutation relation of angular momentum. All right. So formally, you need an S spin half for electron, but it's always half. So that's why very often it disappears, because nobody want to repeat this half all the time, but it's there. And that is the Z component of spin that can take on up, down, or plus, minus half. So formally, a state of the electron in an atom can be classified by this group of numbers. We call quantum numbers, but just, you need those labels. And because this is always a half, the convention is that we are being lazy so that you won't see this half too often. Therefore, you will see 4 quantum numbers. Okay, but for completeness, you have L and ML, you should have SMS. Okay, you're skipping the S simply because of laziness. Therefore, you will see this labeling for an electron state in an atom. And this carry different symbols as we discussed last time. We can do it like this, plus half, minus half, or simple using an arrow, up spin, down spin, or you use a column 1, 0, 0, 1 for the Pauli matrix eigenstate. Okay, the sigma Z. So all this mean the same thing. Therefore, when we have P, L equals 1, S equals half for the spin all the time, you may wonder, the electron has orbital angular momentum, the electron has spin angular momentum. Will it make sense to introduce a total angular momentum J, which is the sum of L plus S? Okay? So for the student who asked the question, here another J symbol comes in, okay? But this J symbol is not about the quantum number yet. It is a vector. We have the orbital angular momentum being formally a vector. The spin angular momentum being formally a vector. Remember, it has X, Y, Z components. Okay? Therefore, line 11, equation 11, we are adding 2 vector angular momenta into a total vector angular momentum. Okay? So that must be made very clear. Okay? About the quantum number of this capital J, that will come next. All right? Now, I haven't proven it here for you, but you can do it easily. This has 6 commutation relations for S. You have 6 commutation relations for L, all right? And L and S are 2 different entities, spin angular momentum, orbital angular momentum, okay? It is easy to show that J also has 6 commutation relations of the same form. You can write it as, the X component is Lx plus Sx and so on. And then when L meet an S commutation relation, they do nothing to each other, okay? I mean, they commute them, okay? And then you can find, you will realize that this is also an angular momentum, all right? Or the simple thing I would say is just exercise your common sense. You have angular momentum put together. Why? How come this not become an angular momentum? Okay, so just do what natural. That's it. That's the easy and sometimes the best way to do physics. Okay. So now, J is an angular momentum. Therefore, suddenly we know a lot of things about J. Meaning, we copy all the results from the last section for the reason and only reason that this is an angular momentum in quantum mechanics. Therefore, we expect the magnitude square to have this form. Okay? The question is, what is this small quantum number J? We have yet to state the rule, okay? But we know that it must of this form and more. The Z component must of this form. And Mj can only be different by 1, okay? And more, given the longest Z component J, H bar, Mj goes from J to minus J in step of 1. And altogether, there are 2J plus 1 values. Okay? So now you realize or appreciate this box. We can immediately write it down simply because we realize that J is an angular momentum in quantum mechanics. And we have proven from the commutation relations, that these are the properties. Okay? And we know a little bit more actually. This J can only take on either integer or half integer. Okay? We have proven that. So now the question becomes, we know this is attached with an L quantum number, small l, I mean, and this for an electron. One electron, for example, is half. The quantum number is S equals half. Then the question becomes, for an electron in P state, what will be the value of J? For an electron in D state, what will be the value of J? For an electron in S state, say ground state 1s, what will be the value of J? Okay, so do you understand the question? The logic flow is important, okay? You know what is going on, moving. Okay? So now I will state the rule for one electron in this atomic state. Hydrogen. So we are thinking about hydrogen at this point. Later on, you have helium. You have 2 electrons. It's slightly more complicated because you have spin angular momentum of electron number 1. You have spin angular momentum of electron number 2. And you have the orbital angular momentum of electron number 1 and electron number 2. Altogether, you have 4 angular momenta. You have to add them together, okay? But if you know how to do 2, you can iterate this rule to do many, okay? That's the flow of logic, all right? For the moment, we only know hydrogen. Let's restrict ourselves to the case of hydrogen's electron for the moment, okay? At least for the next 5 pages, okay? Then we will talk about how to add 2 spin half. So the question is, we have orbital angular momentum, which is a vector now characterized by the quantum number L. We have spin characterized by quantum number S, but if we are talking about 1 electron, it's always this boring half, okay? The question is, we add these 2 vectors, we get a new angular momentum. From our previous result, we know that there is a quantum number called J that we ought to know. The question is, what are the possible values of J? I'm not going to tell you the mathematical derivation because that is in more advanced courses. I give you the result and we apply them for many occasions. That's the idea. So now let me state the rule. So the take-home message is this box. For the hydrogen atom situation, 1 electron, so S is always half. Then we have different states, L, 0, 1, 2, 3, and so on. Now, the rule of getting J, small j, is the following. It can take on L plus half, the half is S. Okay? L plus half and L minus half. But remember, in the general property of angular momentum, okay, the magnitude square, this quantum number J, comes from the highest positive beta maximum, that is JH bar. That is a positive half integer or integer. It cannot be negative, okay? That is an important thing. Therefore, when we exercise this possibility, we have to make sure that the resulting J cannot be negative. But there's one case. If you exercise this one, it will be negative. It is the S state, L equals 0. That is to say, if we exercise this possibility, L cannot be 0. That is to say, for S state, don't use this. For PDF, other states use this, okay? You will get 2 values of J. 2 different values of J, okay? That is to say, for P state, L equals 1, J can be 3 over 2, 1.5, or 1 over 2, half, 0.5. That is 1 plus half, 1 minus half, okay? How about S state? We want positive J only, so only exercise L plus half, that is half, okay? So that is the rule. For the single electron with orbital angular momentum, this is how you get the total angular momentum's quantum number small j. Let's work out an example. Okay. P state. In our previous description, ML is 1, 0, minus 1. This is Y11, Y10, Y1 minus 1, spherical harmonics. And then we have S is half, MS is plus minus half, okay? So all of you know, I think, from high school, that P state actually has 6 states if you include spin. Or in chemistry, you have PX, PY, PZ, you can put up, down, up, down, up, down. Therefore, there are 6 states. Okay? So I hope that everybody knows this. P states including spin, okay? Imply 6 states. You know that, right? I hope that you know that because the next thing need that. Do you know that? Happy with this? You are happy with this statement? Okay. And that is the periodic table. You see? Okay. Now, what we are doing up to now, that is an important physical point here, is we are just relabeling the state. We have 6 states here, and we can try to relabel them, okay? Let's see how it works. If we invoke the total angular momentum J, we have a quantum number small j. We exercise the rule, we have P, L equals 1, add into spin half. The rule says we have two possibilities. J is 3/2 or half. But since it is an angular momentum, the Z component for J is 3/2. There are 4 Z component values. That goes from 3/2 h bar to minus 3/2 h bar, 4 different states, 4 different mj values. And for J is half, we have another 2 states. Mj is half minus half h bar. I mean the Z component, okay? So you see, the point is, if you use this labeling, you have 6 p state. If you use the JMJ labeling, you again have 6 p states. The point is no more, no less. That is what I meant by relabeling the p state. Okay, do you follow me up to here? Is that okay? Okay. So we have some common ground up to here, right? P state, you label it this way, the traditional way, I would say, with L and S separately, you have 6 states. Now I switch the description. I add up the orbital spin angular momenta into a new total angular momentum. I use that description. So I have J and Mj. But I found that all in all, together, there are 6 states. No more, no less. Okay? All right. Now, for those who are more theoretical and mathematically inclined, the following statement, just 10 seconds, and I will not go further into it. Basically, we start off here with 6 states, right? Y11, column 10, that is spin up and so on, okay? And what we are doing is actually doing 6 states into a black box, linear combination, there will be 6 states coming out. No more or no less, of course, right? And when we say we are relabeling, actually mathematically it's slightly more evolved. We are linear combining these states in a different way, 6 in, 6 out. But that is natural. Okay, the number, I mean, no more, no less. Okay, you cannot put in 6 states and get 8 states out. Okay, so that is why no more, no less. But if you understand we are just relabeling things, that is sufficient for many purposes. Okay, then you may wonder, why bother, right? Is any way, one of the way is better? Is one more advantageous than the other? Okay, let's be scientific, physics students. There is no general answer. The good answer is you have to tell me more about the situation that we are considering. So it depends on the situation. Okay, for example, later on, when we see that there is an effect called spin orbit coupling, the spin angular momentum thought into this, the orbital angular momentum in an additional term in the Hamiltonian. So when they couple strongly, that means the entity that comes out as a combination of S and L will be a better description of the physical situation. After all, they couple, okay? Or they mix, they couple into something else, the total J. And that situation using the JMJ description will be advantageous. However, there are other situations where they don't couple that strongly. For example, I buy a big magnet and apply a big external magnetic field. So the two angular momenta will be very busy entertaining my external magnetic field because my field is stronger than the other thing coming, influencing me. So the orbital angular momentum will do whatever it does to minimize energy aligned with my field. The spin angular momentum will do something to align with my field. So they operate kind of independently. Therefore, their coupling is not that severe, that strong. In that case, the traditional labeling will work. Okay? So be scientific. That is another story, another side of this story. Okay? Don't think that you must do that, and that is always better. Not quite. At this point, we're just preparing ourselves for different occasions. We have this, but we don't throw away this. We have both in our hands. Then, depending on which situation, this one is more appropriate, that one is better. Okay? That is what I meant by scientific. Okay? So, this page just summarizes what we did in a table way. For the P states, either we do this labeling, not involving JMJ, okay, just orbitals spin separately. We have this quantum numbers altogether 6 state, or we have P, so we keep the L equals 1. We have the electron being spin half, we should keep the S equals half, okay? But then we don't talk about this MLMS, but we talk about JMJ. We have already seen two values of J. MJ takes on these values, together there are 6 states, no more, no less, okay? An exercise is to think about these states. L is 2, so you will have 2 plus half, 2.5. Then another one is 2 minus half is half, okay? So you see how many states are there together? Does it come up with the D states having 10 states if you do the spin and orbital labeling? It does, of course, right? So a way to think about this rule, okay? Why do we have these two J's values? Okay, this is some physical picture coming in. Why do we have these two? Okay. Now, basically, if you think about it, this gives us the magnitude. Then, in our previous section, we also know that you give me an L that is the longest Z component. So if you give me P, the longest Z component is 1 h bar. If you give me spin half, the longest is half h bar. Now we have some two possibilities in drawing the vectors. 1J is 3 over 2. Right, it's 1.5. It's 1 plus half. Okay. In that case, you can think about it this way. The 1 meaning the Z component of orbital is positive, the bigger one, okay? The half is again the spin. You have this vector model, okay? The spin Z component is also the positive one. Now, if these two vectors tend to be more aligned along the Z direction, okay, or aligned with each other in the general direction, okay? So I'm drawing it here. The L and the S, so they are kind of aligned, at least not opposite to each other in general, so that to make this J the longer possibility, and that will be the case where you have the J equals 3/2 situation, okay? But there are two vectors, I mean L and S. Another case is that, remember the vector model of spin half, you have this cone and that cone, okay? Because you have plus half Z component or minus half Z component, okay? So another possibility is for this S to point kind of anti-aligned with this L. So the sum will be shorter, the J will be shorter, and that is the situation where you have J is half, okay? So if you carry this picture to adding two spin half angular momentum, so you have two electrons, you can imagine there is one case that you will have half times half that gives you as total spin equals quantum number S is 1. They tend to be aligned in general, okay? Another case is that they could be anti-aligned. One spin half in this, like this, another spin half like that, and they always do this. So they cancel each other and you have spin 0 when you add two spin half angular momentum. And that is important in helium atom. You have two electrons in ground state. What is the spin? Is it spin 0 or is spin 1? Okay. The answer is spin 0. Okay. And so-called spin singlet. The spin 1 case is called a spin triplet. We will have something to say about that next time. Okay. So here is a picture of doing the rule, why you have these two values. Okay. But if you don't like this picture, never mind. Just follow this regulation that can be proven more formally in higher level quantum mechanics courses. Okay, so then you may wonder what for. Okay, so let me end this with a hint on what for. We have seen from spectroscopic data that the P state in data actually split into tiny splitted situation. Okay, last time we saw the number, right? 80,000, nearly 90,000 wave number, they are off by 1 centimeter inverse. Okay, that is that tiny split for hydrogen 2p. And immediately we have a way to think about it. Maybe it's the following situation. Inside the hydrogen atom, we have the electron orbiting, thereby it looks like the nuclear orbiting around the electron. But the proton is positive charge, there's a current loop. The current loop generates a magnetic field at the location of the electron. There's no external magnetic field, all internal. Therefore, that magnetic dipole moment with spin has to respond to this internal magnetic field due to the orbiting motion. Therefore, S and L are coupled, and that is called spin-orbit coupling. This will introduce one new term into the Hamiltonian for the hydrogen problem. Since L and S are coupled, we better describe the state, the P state, by J. We know that there's a J 3/2, J half for the 6th state. They split into 4 and 2, 4 state, 2 state. perhaps with this spin orbit coupling, the energy of the J equals half state is different from the energy of the J equals 3/2 state. And that little splitting is due to this additional term of spin orbit coupling. And that is, I think, half of the story about this splitting. Okay? If you want to know another 20% of this splitting, this week's sample question 6, the TA will work out the relativistic correction. If we don't start with Newtonian, we start with relativistic kinetic energy term 1, correction term. That will also be responsible for this shift a little bit. Okay, so that is the story. All right, so I will end today here. Next time, we will discuss how to add 2 spin half, prepare for helium atom discussion, and then we will discuss spin orbit coupling with the emphasis on the physical picture. Okay, so I will stop here today. If you have questions, you are welcome to stay and ask.